Hello and welcome everyone. This is the first lecture here for your Organic Chemistry 1 lecture. So as with like all classes, we want to start off by explaining what exactly our subject is going to be for this semester. So yeah, organic chemistry, what is it? And so we're going to start with the modern definition and talk briefly about kind of the historical definitions of organic chemistry, where it comes from. And yeah, just to start off with, we want to explain that in organic chemistry, we're going to be focusing on the carbon-containing molecules and their reactions. Historically speaking, the word organic comes from life. So it means basically like life chemistry. The chemistry of life was the idea. And this idea kind of separated out two different components. We had the organic world, which was the world of life. And then we had the inorganic world, which is the world of things that weren't alive, things like rocks and air, that kind of thing. And so early chemists and pre-chemists believed that organic compounds were special because they came from life. So they were endowed with this vital force. And that belief was called vitalism. So organic chemistry has deep roots in history because it's basically any material that comes from plants and animals. So anything that's been used as a medicine or another type of practical chemistry that comes from a living thing, that's organic chemistry. It wasn't always called that, but that's what we call it nowadays. So like, for example, people have had headaches and aches and pains as long as there have been people feeling things. And one thing that people noticed, even ancient Egyptians noticed, was when you prepared a tea of willow bark, it helped reduce headaches and fevers and that sort of pain. And that preparation of willow bark actually led directly into our knowledge of aspirin. Aspirin's a derivative of salicylic acid, which is present in willow bark. So that's an example of like an ancient piece of knowledge. We didn't know what the compound was called. We didn't have any structures for it. We didn't know what atoms made it up, for example. We had no idea about that. But it was knowledge passed down by people who had learned the medical effects of willow bark. Additionally, things like soaps, soaps are rendered from fats that are treated with a basic solution like lye. And again, that knowledge has been present in human culture since antiquity as well. It's just something that we've known how to do since before we could write even. So yeah, so that's all examples of early organic chemistry leading into today. Now, unfortunately, things are going to be a little bit harder than that. I'm not going to just ask you to prepare teas or make soaps for me, unfortunately. We are going to have some other things to learn about stuff. So just keep that in mind. So yeah, so talking now modern chemistry, we have organic chemistry and inorganic chemistry as sort of two separate branches on the chemistry tree. There's also like physical chemistry, analytical chemistry, biochemistry that we talk about, but just kind of focusing on the study of different compounds. Organic compounds contain carbon atoms, and that's kind of where we want to start from this. Usually we have a chain of carbon atoms. So we got carbon here. That's one of the 118 known elements. Now, the carbon's going to be bonded all often to hydrogen, especially, also nitrogen and oxygen. We're going to see a lot of those elements this semester, but focusing on kind of the carbon's kind of the most important element if you had to pick one out of all of that. Now, that's not to say that we're going to ignore entirely the rest of the periodic table. We're going to be using phosphorus, we'll be using sulfur, fluorine, chlorine, all the halogens show up eventually in the semester. But for now, I mean, just kind of like laying out our definitions, the compounds we're going to study contain carbon, and that's the main thing. So just to give you an idea, just to kind of get you thinking about this, there are 1.5 million known inorganic compounds. So that's not to say specifically non-carbon containing, but where carbon isn't the main element. So all the rest of the periodic table here, if you add up everything that we know, we've got about 1.5 million known inorganic compounds. So now here's a question. We're going to try to think this through. Extrapolating that, how many organic compounds do you think are known? And again, these organic compounds, they're going to focus specifically on carbon. So think it through. Imagine, what could it be? And if you've got your answer, let's go ahead. 20 million. There are 20 million known organic compounds. I know, it's mind-boggling. Carbon itself is such a special element because this is something that you've known from your general chemistry course. Carbon likes to have 4 bonds. It's what we call tetravalent. Because it can have 4 bonds, it can bond in a number of different ways in an amazing permutations. And again, if we add it up all together, we get 20 million different known organic compounds, compared to just 1.5 million known inorganic compounds. So that's pretty wild. Now, you don't have to memorize all 20 million or anything like that this semester, but by the end of the semester, or at least by the end of the second semester, you should know a good deal about any organic compound that you kind of run across, because we're going to teach you the principles of these. Okay, so one historical note that I like to add in is, again, vitalism was kind of this theory of organic chemistry for a long time. And it was ended in the early 1800s by a student, by a professor, Friedrich Wöhler. He made an experiment where he took an inorganic compound, which was ammonium cyanate, and just by heating it up, he actually formed urea. And urea, of course, is an organic compound. It's something that you're familiar with. That's what's responsible for the smell of urine. So, of course, it comes from living sources. It must be organic, yet we can also make it from an inorganic source. So this kind of gave this showed the lie of the vitalism theory, where, hey, if we can make this organic compound from inorganic sources, clearly there's no longer this separation of this vital force versus non-vital forces. So yeah, okay, so why are organic compounds important? Well, you're here to study organic chemistry, and this organic chemistry is going to show up in just everything that you interact with on a day-to-day basis. So things like your food, your clothes, the medicines that you take, almost always organic chemistry. I mean, there's lithium, I think, is an inorganic medicine, and then everything else is going to be organic, basically. And then plastics as well. The chemistry that makes up our bodies, our biochemistry, is based on the chemistry of carbon-containing compounds. So that's also organic chemistry. So yeah, so that's kind of gives you an idea of the background behind organic chemistry. But yeah, so let's talk very briefly about kind of practically what are we going to do this semester and into the next semester as well. So again, as we mentioned, we're going to study carbon-containing molecules, and we're going to study their reactions. And really, we're going to dig down deep into the question, which is what happens to a molecule during a reaction. We want to understand how reactions occur and the process by which products are formed from reactants. So if you think back to your kinetic theory from your general chemistry class, and we'll review this again later on, but what happens when a reaction occurs? You have 2 molecules, or however many molecules you have, they collide, bonds break, and bonds form. So here what we have is we have a hydroxide ion combining with iodomethane. And what happens is this hydroxide, it's in such a way that it creates a new carbon-oxygen bond. And at the same time, the carbon-iodine bond is broken. It's a heterolytic cleavage. Again, we'll talk about that more when we get there. Hopefully these things kind of like make sense to you here. But that brings up like our fundamental question, like why does this reaction occur? And the long answer, of course, is going to be that we're going to take 2 semesters to explain why these reactions occur. But the short answer, and this is always where we're going to be, this is always the answer to any specific reaction, we're always going to be focusing on the electrons. So that's what we're going to be doing this semester. Oh. Go. And we're back. Okay, and let's end that recording.